In this next section, we're going to go through the difference between relations and functions. So we're going to start by first going through how I can represent intervals in a bunch of different ways. Then we'll talk about the difference between the relation and the function. We're going to talk about the vertical line test and then also go through a different notation that we can use to clearly identify if something is a function. So first and foremost, we have 4 different ways that are kind of common to use to represent an interval. And so what I'm going to do is I'm going to go through each of these using the same x values that I'm going to be talking about. So the first one is one that we've seen pretty frequently, which is our inequality notation. So if we have something like this, 1 less than or equal to x less than 5, you can really read this as you can take all x values that are greater than or equal to 1, but they are less than 5. Okay? So any x value that satisfies that inequality is what we're talking about for that group of numbers. Second thing we can do is a graph or a number line, which we've seen number lines in that last section. We need a couple main values on here. So we've got 0, 1, 2, 3, 4, and 5. Okay. So what we can do is we're going to start at 1 and go to 5. So I'm going to mark these with 2 circles. To say that I can actually equal something, I'm going to go ahead and shade that circle in. So I can actually equal 1. To say I can't equal 5, I'm just going to leave this as an open circle. And then we shade all of the values that we're specifically talking about. So we're taking all the x values between these two. Okay. You can also use different endpoints if you don't want to use a circle. You can also use a square bracket to say you can equal something and a parenthesis to say that you can't. So it's going to be really useful for when we talk about interval notation, but really most common one is going to be using these circles. Now for set builder notation, we're really talking about a set of numbers. So that's why we can call it a set. This one is kind of a little bit different. So really I'm going to just dissect what this means. But basically you have some kind of conditions that have to be true for this number to be in the set we're talking about. So when we start with a brace, this is saying for our sentence, the set of. Then this right here tells us we're taking the set of x values. The bar is meaning the phrase such that. And then at the end, you put whatever conditions you need to hold. Okay, so there might be 1, there might be 2, there could be a ton of them. But all that's meaning is we're taking the x values so that this thing holds. Now the most important notation we're going to use is interval notation. It is the most concise and condensed form. So if I'm saying I can take all x values between 1 and 5, I'm just going to write those 2 coordinates. I'm starting at 1, I'm ending at 5. To say that I can actually equal 1, we use a bracket. So these ones should be nice square brackets here. I'm going to use a square brace to indicate I can include the endpoint. To say I can't equal this, but I can get very close to it, we're always going to use a parenthesis. So you don't want to say from like 1 to 4 and put a bracket around 4 because then you're missing 4.5. That number is in this interval. 4.9 is in the interval. 4.99999 is in the interval. So I need to get as close to 5 as humanly possible. So that's why we put 5 as our cutoff with that smooth parenthesis around it. If our interval happens to continue forever in one direction, you're going to have an infinity in that interval notation. We can never equal either of these. They're not real numbers, so I can't plug them into anything. So we always want to use a smooth parenthesis around that. Okay. When we're talking about multiple sets, because it might be I could take something from this or I could take something from this one instead, we're going to talk about the union of 2 sets. So that's just indicating the word or. I can take something from here or from here. And really the letter we're going to use to symbolize that is a nice U. So let's get some practice. We want to write this at an interval notation, and we also want to graph it. Really, graphing it is going to be super helpful for you to be able to write it in interval notation. So I'm actually going to do that part first for all of these. So for A, here's our number line. The leftmost number we have is -4. The rightmost is -1. So I want to put 2 circles around these, and because I have those bars underneath, we can actually equal them, so we can fill in our circles. And then because I can take all values in between these 2 numbers, we end up shading in the middle. So if we want to write this in interval notation, the furthest left we go is -4, and we can equal it. And then the rightmost we go is -1, and again, we can equal it. For the second one, we actually have 2 different intervals. So I can take x values that are bigger than -3 or x values less than or equal to -7. So between these 2 numbers, -7 is the smallest, and -3 goes here. So if we graph this first interval, I can take x values greater than -3. I can't fill in the circle because I have that strict inequality, but I can take all x values greater than it. For the second one, we can actually equal -7 because we have the lovely bar underneath. And then I can take x values that are less than this as well. So I fill everything into the left. So if we want to write this in interval notation, our first interval, because we're going far left forever, the end point is -infinity. And then we stop at -7 and we can equal it. For the second interval, our starting point is -3. I cannot equal it. And then because we're going forever in this direction, we go to infinity. And then again, to say I can take from this set or this one, we join the 2 together with a union. Okay. For this last one, I have that set builder notation. Really, again, this inequality is the thing that determines what interval we're talking about. So if we go ahead and graph this number line, we only have one important number, 9. I cannot fill in 9 because I have a strict inequality. So I can take all x values that are bigger than this, so we end up shading to the right. So in interval notation, we start at 9 and can't equal it, and then continue to positive infinity. So now that we've got a hand of writing intervals, we can actually talk about what a relation is. And so a relation is a correspondence between 2 sets, where you take something in the first set, which is called our domain, and it's going to get paired with something in the second set called the range. And it could get paired with multiple things. So the key word being here is that it's paired with at least one element in that second set. Okay? So our input values are the domain, the output values are the range. So there's some kind of connection between these 2. A function is much more specific. So if I take something in my first set, the domain, it corresponds to exactly one element in the range. So I can't have an input with multiple outputs. So what you can kind of think of is if we took the student body at Polk, we could define a couple different relations between them. So one of the relations could be the classes that each student is taking. There are definitely people that are taking multiple classes. So my inputs, which is each student at our school, can have multiple outputs. So you could be taking 2, 3, 4, 5 classes. You could be taking one and have a single output, but there's definitely people that are going to have multiple outputs. Now, if instead I define a different relation and I say our students are the input, but the output is their height. There's absolutely no way that someone's going to have multiple heights. You are one set height. So that's going to be something that is a function. The input has a single output. Okay? So let's try a couple different options. We're going to be given some kind of connection between our x values and y values, and we want to determine if it is a function. And then regardless for these, we're going to figure out what the domain and range are. So what's the input, what's the output? So if I look at this first one, my x value 2 pairs with 8. My x value 3 pairs with 8. My x value 4 pairs with 9. My x value 5 pairs with y value 9. So because of this, I'm really concerned about the inputs. I want to make sure the input does not have multiple outputs. And this one's perfectly fine. I have completely unique inputs. So this is a function. Okay. So no input repeats, which is great. The outputs definitely repeat, but that's okay. We don't care about the actual output. We want to just make sure the input does not repeat. So for this, if we're finding the domain, again, this is a set, so I want to start it with a brace. My input values are 2, 3, 4, and 5. When we go to find the range, that's where we look at that second coordinate, which is the output y. You really only have 2 numbers, so you don't need to double dip and put 8, 8, 9, 9. Really, the 2 values in our range are 8 and 9. Okay. For this next one, we really, again, just have coordinate pairs laid out in a slightly different way. So each one of these corresponds to a pair. Like this is -1, 0. This is -1, 1. And this one is -2, 2. So right off the bat, when I look at this input value, because you see my arrows are going out of it, -1 is my input, it has 2 different y values corresponding to it. So this one is not a function. Okay. But that being said, I still can find the domain and range of this thing. So I have 2 inputs, -1 and -2, and 3 outputs, 0, 1, and 2. Okay. This last one, a little bit different. So I really don't have coordinate pairs, but instead I have some kind of equation telling me, here's my x values, my y value is found by this formula. So you might recognize what this is a shape of because you had to have taken intermediate or something equivalent to get here. This is really just a line. So y equals mx plus b. Every single input you have for x, the y value is dictated by this formula. So if I plug in 0, my y value is 3 times 0 plus 2, a single y value. If I plug in 100, my y value is 3 times 100 plus 2. I'm never going to have multiple y values from that same x value. So each x value yields 1 y value by this formula. So this is a function. Okay. When we talk about the domain and range, you also will often see me abbreviate these just as D and R so we don't have to write it out every single time. You have no restrictions on X. You can plug in whatever you want. So my domain is all real numbers, which is -infinity to +infinity. No restrictions. And same thing, if you were to try to graph this and plot x values and their corresponding y values, you're going to have every single y value. So your range is also -infinity to +infinity. Okay. So this is actually leads into another concept known as our vertical line test. So when we're given the graph of a relation, we can use this test to determine if that graph is the graph of a function. And so the idea is you want to make sure that x value does not correspond to two y values. But if you think about fixing an x value, it's a vertical line. So if you draw a vertical line and it hits your graph in multiple spots, not a function. That's all this vertical line test says. So really we're just going to do two quick examples to kind of see that's the case. So looking at this first one, here is my x value that I pick. If I go ahead and graph a vertical line, this would be x is equal to this number. This x value has two different output values. So my vertical line has hit the graph in two spots. So this is not a function. For this other one, however, no matter what vertical line you draw, your graph is going to hit the vertical line in a single spot. So what this is saying is each of these x values has a single output. So this one is a function, okay? So we're going to be dealing with a lot of different graphs of different types of functions. We really want a much nicer way to talk about how can I tell without needing to know the shape or the graph of it, especially when we start to get some complicated expressions. So this line that we dealt with in one of our earlier examples, y equals 3x plus 2, it's a line passing through 2 on the y-axis with a slope of 3. This line is going to pass that vertical line test. So this is a function. So what we do to say that without needing to verbalize the words, instead of writing this y, we can replace it by f of x. So f meaning function. You can call it whatever you want. You can call it g of x, you can call it h of x, you can call it y of x. It's really just naming the function f. So we use this notation to indicate that this is a function of our input variable x. So you don't want to mistake this as multiplication. It's not saying take f timesing it by x. This is saying f of x. So when we write things like f of 4, this is basically saying, okay, what is the y value of the function corresponding to x equals 4? Or you can think of it as f evaluated at 4. So in our original expression, we're going to replace all of the x's we see by whatever we have in here, which in this case is 4. So when I say f of 4, I'm going to take 3, I had 3x, so I'm going to do 3 times 4 plus 2. So that gives us 12 plus 2, or 14. So this is really the y value in the coordinate pair on our graph. So when x is equal to 4, the y value is 14. Okay? So let's try an example. Given this function g of t, so t is the input, which is 4t minus t squared, we want to find the following things. So first and foremost, we want to find g of 3. So looking at our original expression, anywhere I see a t, that was what this input is, I'm now going to replace the t by 3. So we get 4t, so 4 times 3, minus t squared. So I get 4 times the input minus the input squared. And then from here, we just got to actually do this. 4 times 3 is 12, and then 3 squared is 9. So if we take 12 minus 9, we end up with 3. When we deal with a negative number, same thing. Just remember your order of operations. So we have 4 times the input minus the input squared. So this is where it can be really tricky and you can mess up your minus signs. You do the exponents of this first, so you do the input squared, and then you go ahead and deal with that minus sign afterwards because it's just multiplication. Okay? So if we do 4 times negative 2, it's negative 8. And then when we take negative 2 and square it, it's going to give us positive 4. So we really get negative 8 minus 4, which gives us negative 12. So again, for both of these, what this tells us is when x is 3, the y value is 3. Or when t is 3, the y value is 3. When t is -2, the y value corresponding to it is -12. For this next one, we have a lot more algebra that we actually have to do because I have an entire expression in here. So I'm still going to apply the exact same process. We have 4 times the input minus the input squared. Okay. So if I need to simplify this, the first one's not too bad. We can distribute that 4 out. So that gives us 4 times h plus 8. But over here, before I can distribute that minus sign, I have to do h plus 2 squared. So I'm actually going to do that off to the side over here. If I take h plus 2 squared, it's just meaning take h plus 2 and multiplying it by itself. So if we want to do this, we have to FOIL. So our first terms would be h squared. The outer is 2h. The inner is also 2h. And then the last is plus 4. So this condenses to h squared plus 4h plus 4. So really we have to subtract all of that. Okay. And then we do have some condensing. We can go ahead and now distribute this minus sign to everything in here. So this is 4h plus 8 minus h squared minus 4h minus 4. And then a little bit of condensing. I've got 4h minus 4h. Luckily, those cancel each other out. And then plus 8 minus 4. Those combine to positive 4. And then we've got minus h squared. Okay. For this last one, it's really just to solidify the point. If I take g and evaluate it star, all of my t's are going to get replaced by star. Okay. No matter how funky the expression is in there, the entire variable gets placed by the entire expression.